Hello people, welcome to this video. And before starting this, I have a question for you all. Have you guys ever thought what happens behind the scenes whenever you put any of your query in any AI like ChatGPT, Gemini, Claude? How do you get such a well-structured, well-thought response out of it? For example, if you say, "Hi, good morning" to your ChatGPT and your ChatGPT responds back with, "Hello, whatever is your username, good morning." How's that happening? You and your friend both say to your chat GPTs that write me an email, you might get same response and you might get completely different response. So how is that happening? Since when our machines become this smart, this powerful that it is understanding what I'm trying to say in English and responding back to me in English? When did that happen? Because last time that I remember, when I used to miss one semicolon, my machine used to throw an error. So what is exactly happening behind the scenes? It's okay if you have never thought about it, because in today's video we are going to see GPT from scratch. And I'm your host for today, so let's just go. So let's understand. I think that's enough question to start with. Let's understand everything from a customer's perspective first. A customer does not give a damn about what is happening behind the scenes. He is just interested in his input and the response that he is getting. He does not want to know what is happening behind the walls. Right? But as a developer, let's say if we are a developer and we are building one application that will take some input and it will generate a form out of it. Right? So how are we going to do that? For example, let's say if we move the form from here and I want that I give my input to one LLM in my application and somehow I get a very well written form with all the questions, all the input fields, everything. That's the developer's duty. But can you see one thing here? Even this developer does not know what is happening behind the scenes. He just made one application in which you input and on the basis of the output, you get a form. So see, the developer also knows till here that we input something. Now what we are inputting is in developer's hand and we output something. Now how the output is being converted in form is in developer's hand. But even the developer does not know when we input something, how is this LLM outputting stuff. So by this we can classify AI in two different parts. Let's just classify AI in two different parts. First is application. First is application. And second is research part. All the companies like OpenAI, Google, Anthropic, they mostly work here, and we as a developers, we work here. Now today, what we want to say is we want to see this black box. What is happening inside and how are we getting this output? We are interested in that for today's video. This is going to be the first video in introduction to Gen AI series on this channel. So stay tuned because this is the first and last video where we are going to talk about internals of LLM. So let's just see. Let's understand this app versus research field by an example. Assume that you're a worker in a factory that makes solar lamps. This is a solar panel and this is a lamp. Do you know that somehow when sun rays are in contact with the solar panel, this solar panel generates some electricity and our bulb glows. This is what we know as a manufacturer of this bulb, but we do not know how the sun rays are generating electricity. Now, if a person that is working in the solar panel manufacturing factory, he knows because their job is to make solar panels, right? So here we, as a developer, we are this And people working in OpenAI Anthropic are this solar panel is nothing but our LLM, or we call it AI. LLM is basically large language model, and we as a developer use this LLM as a leverage, and we build application on top of it. See, because using this electricity, we can make lamp, we can make cars, we can make anything, right? So that's in developer's hand, and this is research part. I hope that's clear. So let's just move forward and let's see what black box are we actually facing. So if we are inputting something in this black box and we get some output, we only know that we call this LLM. That's all we know about it, right? For example, if I say, "Hi, how are you?" and it responds back with, "I am good." It responds back with, "I am good." So how is it happening? Is a machine which barely speak numbers is able to understand what I'm saying in English? Obviously not. So the first part that comes here is LLMs have their own vocabulary. Yes, LLMs have their own vocabulary, and this vocabulary has words that we call tokens. Tokens. See, now a token can be a word. It can be a part of word. It can be punctuation mark. It can be anything. It totally depends on how the LLM model is trained, how the LLM model is made. It totally depends on these people, how they made their LLM. Perfect. Every LLM has different vocab. Every LLM process the text that we are inputting differently. So, for example, let's say a token here is hi, how, and are, and you, and there is one exclamation mark. This is also token. Perfect. So how many tokens do we have? 1, 2, 3, 4, 5. Now, again, the same question. Is our LLM going to understand this? No. See, what are tokens basically? When we talk about this vocab, what I mean is hi is mapped to some kind of number. Hi is mapped to some kind of number, let's say 3, 4, 5. Same goes with how are you. These are mapped with some kind of number. Perfect. So here when we write hi, how are you, it will be converted in some random numbers. Let's say this. Now, if a human will try to read it, he won't understand anything because this is not English, but a machine can now process it. So the next part, and this part of converting the input and token is called tokenization. I'll keep writing the stuff here. Tokenization. So we have done tokenization. Now, even these numbers are not good enough to make meaning out of it, right? So, so here comes the embedding part. Now what happens is our LLM can convert these numbers into vectors. Vectors. So what is a vector? It's nothing but just the positional encoding of these tokens. For example, if I say hi, let's say this was 234, and after embedding, it was converted into minus, and 0 point, it was converted into this, right? There can be so many positions for every token that we don't know, because LLM actually operates on very deep level of mathematics. I can't actually write the full vector of any word here. So after this tokenization and embedding, finally our word now carries some kind of meaning. For example, this number might be a grammar score, which is very low in my case, and this number might be a nature column. This number might be, um, let's say, greeting. Can be anything. Let's just actually swap this. That will make more sense. So basically in vector, these numbers represent something so that our LLM will know what number means what, right? Now inside this LLM, after positional encoding, we have another layer that we call transformer. And yeah, I'm not talking about Bumblebee. We call this transformer. And what is a transformer? It is an architecture that was given by Google in the research paper Attention is All You Need. If I search for it, attention is all you need. This was the, sorry for flashing, this was the research paper that was published by Google. And here we have the transformer architecture. See, what we have done till now is input, and we have created input embeddings. Now the transformer architecture takes place and we finally get some output. So we'll understand that. Now what happens is, what was our input? Hi, how are you? This was our input, right? Let me just copy this one. See, now these are tokens. When we pass it to the deeper layer of LLM, where transformers are, our AI does not know how are these placed. These are all tokens, right? It can be are, you, how. It can be how, you, hi, are. It can be anything, right? So the next step after this embedding is to create positional encodings. This is basically telling our model that, hey, listen, this is the position and we do not want to mess with it. Remember this position. So remember this position. Now that's how our LLM knows, yeah, this is the correct position and I have to process it in this and maintain context like this. Now what happens next is self-attention. What is self-attention? We are going to see this in deep just in a bit. But let me tell you from a top view, it's basically a mechanism where we allow these tokens to talk to each other to build the context. Which words need more emphasis, which word makes more sense. Basically giving the context about this whole sentence to our LLM, which cannot understand English, but we're trying to make it understand using numbers. Now after this self-attention thing, our LLM is ready to generate responses. Now what happens next is, let me just write all the things here. What happens next is we try to predict our output. Our LLM basically on the basis of the scores that are given to our vector by our LLM generates the score, and on the basis of that we predict the output token. There can be many tokens that are likely to come after it, like how, I, we. There are so many things that can come after it. Let's say how score is 25, V score is 25. Let's just make it 24 and 27 this, and this one is 49. So what is most likely to come is I. Now what an LLM does is it rolls a dice. Yeah, it rolls 100 face dice. It rolls 100 face dice. Wherever this dice land, for example, it landed in 48, then I is the next token that we are going to output. If it lands on 49, let's say, still we get the I. If it ends on something else, we get V. If it ends on something else, we get how. And this process is what this is called sampling. Perfect. So how are you was our input and we got I as output. Now what happens is this whole sequence is again passed to our what? Our LLM, our black box. This whole sequence is again passed to a black box, and that's how we generate the second response, M. And again, this whole thing is passed to our black box to generate the next output, that is I am good. And this thing repeats till we get the end of string token. This is a special token that lies inside the LLM's vocabulary. When LLM is sure that there's no new thing that has to be in the sequence later, it generates the end of string token. And this is where the loop breaks. So that's how LLM generates output. Now, why vectors? Because it is easier for LLMs to predict words in the vector space. Not for us, but yeah, let's see this visualization right here. See, these all are words, vectors in a 3D space. See, that's the capture, that's flower, that's ocean. There are so many words. Our LLM predicts words out of this vector space, and it's again different for different LLMs. But yeah, the point that I was trying to make here is our LLM knows better how to predict words using this architecture through a vector space. That's why we're using that. Now, there's one more term called Softmax. What is this? See, as I said, all of this is just mathematics. Our transformer model generates raw scores, which is again converted into percentage by Softmax. Percentage like how? For example, if let's say 27, 49, 24 that I said, these were raw scores first, and Softmax converted them into percentage. Now, on the basis of this, we are rolling the dice. We have allocated, like, let's say 49 to out of 100, we have allocated 49 phases to I, 27 to how, and 24 to V. The one which lands will be the output. Now, there's one more term called temperature. This is what that decides the randomness and creativity of the output. If this is standard, let's say 0.8, it will be like all right, not very creative, not very predictable, but just all right. And if it's low, like 0.4, then it will be predictable, less creative, right? And if I increase it, then it will be non-predictable, and LLM will try to generate creative responses. It will go random. It might not generate what we wanted it to generate, but yeah, the range of the output probabilities will increase. So that's what a temperature is. Now, let's understand all of this in mathematics using a simple example. And don't be scared, it's going to be easy. And I swear, if you watch this and if you understand this, you don't have to watch any video explaining LLM later if you're a developer. Perfect. So let's just start. Again, I'm saying don't don't hate math, it's a good subject. So let's say we have an input that the bank of river is. Perfect. This is our input. So what's going to be the step one? Tokenization, right? As we discussed, the first step is going to be tokenization. Perfect. So let's just tokenize these words. Let's say the first token here is the, second token is bank, third token is off, fourth token is river, and fifth token is. Perfect. So what happened is these are converted into some numbers. Let's say this is converted into, right? Now, what is step 2? Step 2 is embedding. Now these numbers will be converted into some vectors. Let's say D was converted into 2.0, 3.1, and right, this was D. Like that, these numbers will also be converted into some vectors. And if we arrange that together, we'll have a input matrix, right? And we can call this matrix, let's say, let's just call it X. X will be our input matrix. So for example, I have this input matrix here. Let me just grab this and put it. Don't be scared, guys. So after embedding, we have this input matrix here and we'll call this x equal to this. Perfect. Vector embeddings of these 0.80, 0.00, 0.20, bank is 0.20, 0.50, 0.30, off is this, river is this, is this. First column is representing grammar, second column is representing finance, third column is representing nature. Again, this is for example purpose. In reality, it's not only three positions, it's a lot. Maybe I can't even write here. It's like generally a lot. So see, D is a grammar word, that's why its grammar score is high. Bank, its finance score is high, nature score is like low. Off is a grammar word, is a grammar word, river is a nature, right? So this is our input matrix. Perfect. The next stage was positional encoding. So we'll do positional encoding, and after that, step 3 was positional encoding. Let me just write it here. Positional encoding. After that, our input matrix will change slightly, but to keep it simple, let's just keep it as is. Now let's move to the next step. So what's the next step? The next step is self-attention. Okay, self-attention. This is where things get interesting because self-attention actually lies in this transformer model. See, we have done inputs, we have done input embeddings, we have done positional encoding. Now we are stepping into this zone. Perfect. Now to make it more complex, I'll not open that transformer page again. So self-attention, what actually happening here is we are giving our tokens a mechanism to talk to each other in order to build context out of our sentence that will feed to LLM to generate better output. Perfect. So how is that going to happen? So in self-attention, what happens is our LLMs now basically have pre-trained weights. What are these? These are nothing but just a grid, or you can call it tables, that represents key, query, and value. Perfect. These are the three things. Just the table that we have. Let's say this is some table 1, this is some table 2, this is some table 3. What is WK? This is key weights, right? This is responsible for telling what word carries which attribute. So we are going to multiply this WK table with our metrics to get our key metrics. Perfect. What is WQ? This is query. This is basically responsible for telling our LLM what a word is asking for. WQ query is self-explanatory and W is value weight. This basically tells our LLM which word carries which semantic meaning. So with the help of this, if we multiply x with WK, x with WQ, x with WV, we'll get three matrices K, Q, and V. See, what are we trying to do now? In this step is we are trying to obtain raw scores that our LLM will generate. Perfect. Through which we'll make this percentage thing that we explained here. Yeah, this percentage thing, which word from output should get the chance to be outputted, right? So for simplicity, we'll consider that these matrices after results are equal. So how are they calculated? See, let me just put it here. We took this matrix X and we multiplied it with the weights that we already had in our LLM. Perfect. So that resulted in this. So now we have our new matrix after multiplication of weights as this. This is Q equal to K equal to V. So are we done? No, not yet. Now what happens is our raw scores are what? Our raw scores are actually multiplication of our Q matrix and transpose of key matrix. Perfect. What is transpose? Nothing, just the matrix flipped. So let me grab that from here. Yeah, our raw scores would be Q matrix. This is our Q matrix. Actually, I put the wrong matrix in, and that is our K equal to Q equal to V. Perfect. Now our raw scores is nothing but Q into transpose of K matrix. Q is what? Query matrix. K is what? Key matrix. Right. So let's just do this multiplication. Here we have Q matrix, and here we have transpose of K matrix. K matrix was the same thing. If we just flip it like this, 0.80, 0.20, 0.90, 0.70, and yeah, so that's how we take the transpose, and if we multiply it, we'll get the raw scores. So what are our raw scores? Raw scores are this. We got our raw scores. Now, what we are going to do is to stabilize the mathematics, to stabilize, because see, here we just did three columns, right? But in reality there's not just three columns, there are so many columns, and the difference can vary by a very big margin. So to normalize that, we do divide it by root dk. What is root dk? This is nothing but the dimension of the key matrix, right? Here the value of see, in K we have three columns, so the dimension would be 3 in this case for the dk. And this is our scaled attention score after dividing by root dk. Now, what's the next thing? We got the raw scores. Now we want our final scores. So as I said, we'll use Softmax. Softmax was what? It was nothing but just a function that converted raw scores into probabilities, which basically adds up to 100%, right? Right now, we don't know if this add up to 100, this add up to 100, but after softmax, it will be. So softmax takes some input, it takes some input, and it generates our final matrix. Perfect. So after passing our input, this scaled attention scores and softmax function, we get this output. And we'll call this, let's just call this O. This is our O matrix. Perfect. So this is our attention weight matrix after softmax function. Now we want to make it contextualize. So we want contextualize output matrix, right? So what we are going to do is we'll multiply this with our value matrix that we had. Where is our value matrix? K equal to Q equal to V. This is our value matrix. So we'll multiply this with this. Let me just take it here and we'll perform the multiplication to get our final matrix for the stage. And that would be this new matrix after all the calculations that we've done. This is the output. So these vectors right here have context of each and everything. See, you can see that in bank, the finance number dropped 2.15 because after contextualization, it talked to River and now it knows that the bank is not related to finance, it is related to nature. That's why it's 0.30. See, that's how the context is built. And we'll call this final matrix as OF. OF. Perfect. Okay, let's move forward. So we have our OF. What's the next step? Self attention is done. The next step now is FFN, that is feed forward network. See, we just have generated contextualized matrix. We have not predicted any new word yet, right? So in feed forward network, what happens is we generate up projections of this final matrix that we got. So what we do, see, our LLMs have predefined weights for up projection. So we multiply it with up projection weights. What that does, see, right now we have grammar, finance, and nature. By multiplying it to up projection weights, we'll have a big matrix with so many columns that will carry different type of meanings. Let me just grab that matrix, and yeah, so this is the result of our up projection matrix. Perfect. Now the next step is activation filter. Activation filter. What is this? This is nothing but just the mathematical function that will normalize this big matrix that we have right here to actually mute the thing that we do not need and amplify what we need. Basically, if something has a negative score, we mute it. If something has a close to zero score, we mute it. But if something has a positive score, we keep it up, right? That's how what we're doing. We are suppressing the unnecessary information that we made after up projection matrix and we get a cleaner up projection matrix. So how do we do that? There's mathematical function like ReLU or SwiGLU we call it. These are responsible for this. ReLU is the older one. It basically acts like on off switch. And SwiGLU is the new one. ReLU was like used in previous OG GPT models and SwiGLU is the new one. It does not directly turn it on or off. It directly does not mute it. It gives it some score. It's like a graph. For example, if I try to draw a difference between it, you can imagine ReLU like this DC circuit, and you can imagine SwiGLU like this. It's a curve. So it gives some score instead of directly muting it. Search about it more if you guys are interested, but I won't recommend if you're a developer. What I'm telling you right now is just more than enough. Perfect. So after this activation filter, what happens is now we have a clean matrix. Now we'll do down projection, right? Let's say there are 12 rows and these 12 are um, these 12 there are 12 columns and these 12 columns are representing different natures, right? Now what we're doing is we'll compress that 12 different natures into 3 unique natures and we'll use that matrix. Perfect. So just like up projection weight, our LLM has down projection weights also. So we'll just multiply this. So we'll just multiply this with down projection weights to get our matrix, our down projection matrix basically. And that is this. This is our down projection matrix. See, till now, what we are trying to do is we are trying to get raw scores, after which our LLM will pick anything after sampling to show as output, right? We have done tokenization, we have done embedding, we have done positional encoding, we have done self-attention, and we got a really good OF metrics from that. Now we are doing feed forwarding. After this, the final metrics that we get is full of context and full of reasoning and depth that we get from feed forward network. So this is the metrics that we got. Now, to not lose the information that we had in starting due to these multiple steps and this activation filter, what we do is we add this OF matrix. We add this OF matrix to our down projection matrix. This is called, we add this here. This is called residual connection. This is called residual connection. Now, after adding this, we have a matrix. There it is. We did add it and we got our final matrix from this. Now we do the normalization. What do I mean by normalization? Now what we want is the variance in this matrix should be 1 and the mean should be 0, which means these should add up to 0 and it should lie between -1 to +1. Perfect. So after doing normalization, we have our final matrix that looks like this. This is our normalized final matrix. Perfect. Now, like we are almost to the end. We're almost to the end. Now, after getting normalized final matrix, what we'll do is apply temperature. How to do that? We will multiply. We will multiply our temperature scores to it. For example, right now, let's say these are the output possibilities, and we have, let's say finance is -3.5, muddy is 7.0, green is 4.0. We multiply our temperature with it, whatever our temperature value is. For example, if I have temperature 0.04, this will lower the scores obviously. This is what? This is the raw logics of our outputs that we have, that our LLM predicted, right? Temperature will cause a variance in this, and this will make our LLM more creative or less creative accordingly. Now, after temperature, we do final softmax. So now we apply our final softmax here. What we do is we have softmax and we use it to raw logics. It converts our raw logics into percentages. Now we can do sampling. We can throw our dice. Next step is sampling. Sampling will happen. 100 phase dice will be rolled out. 95 phases will be given to muddy. Almost 5 phases will be given to green, and 0 phases will be given to finance. So muddy can come and green can come based on the output of this sampling. Based on the output of this sampling, anything can come, and that would be our output. For example, our input was the bank of river is, the bank of river is, and our output prediction is muddy. So we'll write muddy here, muddy. Now what we did will again happen to this sentence. This will run so many times till our EOS is generated. EOS, end of string token, that is in again LLM's vocab. our LLM will decide when to generate this and when to not. When our EOS generated, the output stream will stop. And that's how LLMs work. I hope that made sense. And if you guys are able to understand like even 50% of it, 60, 70, it's fine. It's good enough. That's enough if you're a developer, and if you're on research part, then you're on a wrong channel. But all right, I hope you guys get the idea. Now, the next thing that we'll do is we'll write a hello world program in our AI world, in our AI series. So let's just make, let me just pin my new Vim first. And here I'll write the code. Okay, let's do a npm init first. Npm init, so that we get packet.json. Perfect. All right, now here we'll import OpenAI from OpenAI. Let me just install OpenAI. Yeah, and let me just change the type to module here. Okay, OpenAI is installed. Now we'll make a client that will be new OpenAI, and we'll write our API key here. For now, I'll say. And if you are not using OpenAI's API key, if you're using something different and you have a base URL, you can write your base URL here too. Base URL. Perfect. Now we'll create a response that will be await. That will be await client dot responses dot create, and we will define our model here. Let's say GPT 4o for now, and we'll define our input. Let's say the bank of river is. We'll just try to print the response here, and let me write API key. Okay, so I've set up the env file. Yeah, let's try to run this AI env file ai.js. Let's see what happens. See, we got some output, but let me just use a mini model here. I don't want to waste my credits. See, we got some object-like structure that is not exactly an object, but yeah, output text is this. Okay, so we got this response from the bank of rivers with GPT-4o mini model. The bank of rivers refers to the land alongside the river's edge, and here it created end of string, and that's when the loop stopped. So I hope you guys like the video, and this program is like a hello world of your AI world, right? So yeah, I hope you guys like the video. If you like this, then drop a comment, and if you like it, then subscribe and like. Alright, see you later. Have a nice day. Bye bye.